welcome to another episode of CHE 101. This segment is about reheat and regenerative cycles, a topic in chemical engineering thermodynamics. First, I will be discussing the theories, which include a recap on the Rankine cycle and the discussions about the ideal reheat Rankine cycle and the ideal regenerative Rankine cycle. Next, we will have the problem statement, after which we will discuss the solution, and I will summarize the topic later on. For the prerequisites, for this topic, you need to learn about the steam tables, i.e. how to interpolate the data, and of course, the Rankine cycle itself. So here we have the ideal Rankine cycle. So shown in the diagram, it is a vapor power cycle that fixes the impracticalities of the Carnot cycle. In the Carnot cycle, it only involves isothermal and adiabatic processes, which involve mostly saturated liquid-vapor mixtures, which degrades the machinery, especially the turbines, which cannot handle moisture. Therefore, the processes are handled isobarically instead. So it is composed of four stages. From 1 to 2, the water is compressed in a pump. Secondly, from streams 2 to stream 3, the water is boiled isobarically wherein it turns into vapor. From stream 3 to stream 4, it is then expanded in the turbine. And then lastly, from 4 to 1, it is condensed in isobarically in a condenser. So the states of the water are: from stream 1, it is a saturated liquid. In stream 2, it is a compressed or subcooled liquid. In stream 3, it is superheated vapor, and stream 4, it is a saturated liquid-vapor mixture. Isentropic means that it is reversible, or if it is indicated, well-designed, and then it is also adiabatic or insulated. Take note that we are only discussing the ideal Rankine cycle. Furthermore, this cycle can also be improved by two ways. One, which is increasing the heating temperature in the boiler, which can be done by either superheating the liquid or increasing the operating pressure. And the other method is decreasing the condensation temperature. Both of the steps will increase the efficiency of the process. Specifically, we will talk about increasing the operating pressure of, of the boiler. Another characteristic of the Rankine cycle is that when heat is transferred to the working fluid in the heater or the boiler, the working temperature is usually low, which means that the cycle is not efficient enough. Therefore, we introduce the ideal regenerative Rankine cycle. This cycle introducing reheating stages, wherein before feeding into the heater, the feed water or the compressed water is heated by the steam which is extracted from the turbine. There are two methods in regenerating, which are open feed water heating or closed feed water heating. So there we have the open feed water heater or the OFWH. This method allows for the mixing of the working fluid, meaning that steam mixes with liquid. So steam at an intermediate pressure is extracted from the turbine, which can be seen in stream 6, and then it is mixed with compressed liquid or stream 2 to produce saturated liquid or stream 3. Keep in mind that this process is isobaric, meaning that the streams that enter and the streams that go out all have equal pressures. So P3 is equal to P2, which is also equal to P6. Next, we have the closed feed water heater. This method does not allow the heating steam and feed water to mix. So as you can see, the steam and the feed water go at different tubes or different pathways. Steam at an intermediate pressure extracted from the turbine, which is stream 7, heats up the feed water or stream 2, which is also compressed. There, there is a mixing chamber for the two compressed liquid streams that travel to, to the boiler. The steam is condensed to the saturation point or 3, meaning that the temperature of the steam that is condensed is equal to the condensation temperature at saturation, which is equal to the outlet temperature. The feed water is then heated to the condensation temperature of the steam, as I have mentioned before. And again, keep in mind that the pressure is equal for what goes in and what goes out. Therefore, pressure 3 is equal to pressure 7, which is the steam that condenses. And then P2, which is what comes out of pump 1, is equal to P4, what is after heating, which is P9 after mixing, which is equal to P5 after mixing, which is equal to P6, which is the thing that goes out from the boiler, the vapor. So therefore, you can easily find the characteristics of them from the steam table. It is also important for you to know the fractions of what is extracted from the turbine for what is used for reheating and what is used for the condensation process. For this, we need to take note of the material energy balance in the feed water heaters. So the summation of the product of the mass flow rates and the specific enthalpy and the difference of that of what goes in and what goes out is equal to 0. So keep that in mind. Now we have our problem statement from Sengel et al. 2011. A steam power plant operates on an ideal reheat regenerative Rankine cycle with one reheater and two feed water heaters, one open and one closed. Steam enters the high-pressure turbine at 15 megapascals and 600 degrees Celsius, and the low-pressure turbine at 1 megapascal and 500 degrees Celsius. The condenser pressure is 5 kilopascals. Steam is extracted from the turbine at 0.6 megapascals for the closed feed water heater and at 0.2 megapascals for the open feed water heater. In the closed feed water heater, the feed water is heated to the condensation temperature of the extracted steam. The extracted steam leaves the closed feed water heater as a saturated liquid, which is subsequently throttled to the open feed water heater. Show the cycle on a T-S diagram with respect of the saturation lines, determine the fraction of steam extracted, the thermal efficiency of the cycle, and then the net power input for a mass flow rate of 42 kilograms per second through the boiler. So as you can see, we have all of the reheat and regenerative cycles combined. To start off with this problem, we need to list down the given parameters. So as mentioned in the problem, we have for stream 8, the pressure is 15 megapascals and 600 degrees Celsius. Stream 10 is 1 megapascals and 500 degrees Celsius. Stream 11 is 0.6 megapascals. This stream 11, is used for the closed feed water heater. Stream 12 for the open feed water heater has a pressure of 0.2 megapascals. And then the stream used for the condenser is 5 kilopascals or 0.005 megapascals. Again, here are our required parameters. To streamline this problem, we need to list down our constants. That is, what are constant in the processes. So first we have pumping, which as we all know is isentropic. So S1 is equal to S2 and S3 is equal to S4. The next one is for the turbines or for the expansion, which is also isentropic. So S8 is equal to S9, and then S10, which is what enters, is equal to S11, S12, and S13. P3 is equal to P2 is equal to P7 is equal to P12, which is also equal to 0.2 megapascals, accounting for the open feed water heater. As I have mentioned, the open FWH is isobaric, meaning that the pressures are all equal. And the second one is P11 is equal to P6 is equal to 0.6 megapascals. So the steam that reheats stream 4 is isobaric, meaning that what goes in and what goes out, it's isobaric. Again, for the closed feed water heater, P4 is equal to P5 is equal to P8. So aside from the closed feed water heater, P5 is automatically equal to P8 because of the boiler. The boiler operates isobarically. So P13 is equal to P1, which is equal to 0.005 megapascals, which accounts for the condensation process. And again, for the boiler, for the reheat cycle, P9 is equal to P10, which is equal to 1 megapascal, the outlet temperature of the reheating boiler. We have a throttling valve. Throttling processes have isenthalpic changes, meaning that the enthalpy is equal. Therefore, H6 is equal to H7. And lastly, the condensation temperature of stream 6 when stream 11 is condensated is equal to the outlet temperature of T5. So first, we should prioritize the streams that have given pressures and temperatures, especially when they are at one state, like for example, superheated vapors, and more especially if they are saturated liquid or saturated vapors. Usually, we could only calculate the saturated liquid vapor streams last. So for the properties of stream 8, which is as SHB or superheated vapor, so we have obtained these parameters from Keenan and Kay's steam tables or the thermodynamic data for water, which includes the, the properties for saturation point, vapor, and of course the compressed liquid or just liquid. Keenan and Case, I am referring to the green book that we usually use in Chaterm. So as we can obtain in the book. So we have the specific enthalpy and the specific entropy. So I have given the units which are in kilojoules per kilogram and kilojoules per kilogram Kelvin. So I will not give these units anymore, but keep in mind that the units in these solutions are all dimensionally consistent. So we can get the properties of of stream 8 and stream 10 on from the table. Note that for stream 10, the entropy is equal to S11, S12, and S13 as we have mentioned before because of the isentropic property of the turbine. For stream 9, which is also an SHB, we can deduce that P9 is equal to P10, which is equal to 1 megapascal because of the reheating boiler, and S9 is equal to S8 because of the turbine. At 1 MPa, we can extract these values. So we need to interpolate these values so that we can get the properties which are the temperature and the specific enthalpy. Do note that during this video, all the text highlighted in green is the type values, meaning that we got these values because of the properties of the processes. And usually these are helpful for interpolating our needed values. And then the values highlighted in red are the interpolated values, what we have calculated from the interpolation process. And the text highlighted in blue we got from the table, the green book, the Keenan and Keys theme tables. Since we have the specific entropy for stream 10, we can get stream 11 and stream 12. Not stream 13 because it is an SLV and we need to get some more data which we can do later on. So for stream 11 or SHB, the pressure is 0.6 megapascals and the specific entropy is 7.7622. For 0.6 megapascals from the steam table, these are the properties. And then with the tie value of 7.7622, we can get the temperature and specific enthalpy. We can also do the same process for stream 12, only this time we can only get the properties at 0.2 megapascals. I will not discuss the interpolation process nor the how to get the values from the steam table since I expect that you have learned it either from your class or from the video in the channel. Moving on, we have stream 1, which is a saturated liquid. So getting the properties from this would be straightforward since it only exists in one phase. So the pressure is 5 kilopascals and the saturation temperature of stream 1 is 32.88. And then we have the enthalpy and the entropy, which is extracted from the liquid phase values from the saturation table. So we need to get the saturation properties, specifically the entropy and the enthalpy for the liquid and vapor states as tabulated in the table, those in blue. We need those values to get the properties for stream 13, which is shown below. So the temperature for stream 13 is also equal to the saturation temperature as well as the pressure because of the process. To get the values, we need to get Y or the vapor quality, which is the relative amount of the gaseous phase. So for that, we can use the tie value, which is entropy 13, which we got from stream 10, which is 7.7622. It is equal to the summation or the weighted sum of the entropies of the vapor and liquid phases, from which we can get the vapor quality of 0.9201. Then we can use the same reasoning of the weighted summation to find the total enthalpy of stream 13, which is equal to 2367.8. Now we have the second stream after the compression of stream 1. So stream 2 is a compressed liquid, meaning that we need to get the properties from the liquid table from the green book. So at 0.2 megapascals, we have 0.2 megapascals because of stream 12. And as I have discussed before, all the pressures around the open feed water heater are all equal. And the entropy is 0.4764 as we have obtained from stream 1. So we can notice that 0.2 is not listed among the pressures in the compressed liquid table. Therefore, we need to double interpolate our values. So first, using the tie value of 0.4764, we can double interpolate starting with 0.2 as the tie value to get the entropies basing on the endpoints of 0 and 2.5 megapascals. Then we can obtain the values for the specific entropy at 0.2 megapascals. After which we can calculate the temperature. So from the table, we have the endpoints of 20 and 40 degrees Celsius. And with that, the temperature is 33.04. After that, we can use this value to get the enthalpies at 0 and 2.5 megapascals via interpolation. And then using the pressures, we can get the specific enthalpy, which is 138.64. Then we have the third stream, which is a saturated liquid. P3 is equal to 0.2, again because of the open feed water heater. And T3 is a saturation, which is 120.23. H3 and S3 are as follows. And S3 is equal to S4 because of the pumping, which is isentropic. Stream 4 is a compressed liquid. As I have mentioned, pressure 4 is equal to the pressure of the boiler, and which is 15 megapascals. So at 15 megapascals, which is thankfully included in the compressed liquid table, we can simply interpolate the values as shown in the table, from which we have the temperature and the enthalpy, which are 121.49 and 520.48 respectively. Next, we have the sixth stream, which is before the throttling process, which is also a saturated liquid. P6 is equal to 0.6 megapascals, which is equal to the pressure of the stream 11 from the turbine. T6 is equal to saturation temperature is equal to 158.85. Keep in mind that this is also the outlet temperature of the closed feed water heater, meaning the liquid form, which is stream 5. The enthalpy of 6 and is equal to 670.56, which is equal to the enthalpy of stream 7 since it undergoes a throttling process. Therefore, the process is isenthalpic. S6 is 1.93, and we now have stream 7, which is a saturated liquid vapor mixture. As we have obtained from the stream 13, we need to get the vapor quality. So P7 is 0.2 megapascals, T7 is 120.23 degrees Celsius from the saturation table, and then we need to get the weighted sum, which is 670.56, to get the vapor quality, which is 0.0753. And from that, we can get the specific entropy of stream 7. Lastly, we can get the properties from stream 5 using the properties that we have obtained so far. P5 is again equal to P8, which is the boiler operating temperature, which is 15 megapascals. And the temperature for stream 5 is equal to 158, which is equal to the condensation of stream 6. At 15 megapascals from the liquid table, we have these properties. And from the temperature, which is our Thai value, we can get the entropy and the enthalpy. So now we are finished calculating the properties of every stream. And from that, we can calculate the fractions of the extraction from the turbine, which are stream 11, stream 12, and stream 13. So again, as I have mentioned, we need to get the material and energy balance. What goes in minus what goes out is equal to 0. So first, we need to consider the closed feed water heater, which have only 4 streams. So M4, M5, M11, and M6. So M4 is equal to M5, which is the overall stream. That is, M4 is equal to the totality of what goes in or what goes out. And M11 is equal to M6 is equal to YMB5, M5. That is the fraction that is extracted from the low pressure turbine. So we can derive the formula for Y, and then from that we can calculate the fraction, which is 0.06019. And then from that we can calculate the values for the open feed water heater, and the streams are 12, 2, 7, and 3. So M2 is equal to 1 minus Y minus C, which is X, which is equal to the amount that we have obtained for the condenser. M7 which is equal to Y, and M12 which is equal to C. Take note that M7 is equal to Y M3 because stream 7 comes from the throttling process of stream 6, which comes from the stream 11. So again, from the material balance, we can derive the formula for Z, which is the fraction that we have extracted from the OFWH, which we can calculate to be 0.1168. And then we can get X, which is the condenser fraction, which is 0.8230. We can summarize the properties that we have obtained from the previous slides in a table. So there we have empty stream from 1 to 13, as well as the properties, which are the temperature, pressure, entropy, and entropy. We can also list down the mass fractions, which we have obtained from the material energy balance. From this, we can calculate the net enthalpy, which is useful for calculating the work and power. We also have the Y, which is the vapor quality as well as the states of the water during the processes. On the right, we have the TS diagram, which shows the entirety of the process. So now for our last steps, we need to calculate the energy extracted or received by every processes. So for the pumps, we need to make sure that the net enthalpies are positive, meaning that they consume power. So for pumps 1 and pumps 2, we have to get the difference between the enthalpy of what goes out and the enthalpy for what goes in. This is true for every power or energy stream. So H2 minus H1, for example, is 0.6749, and H4 minus H3 is equal to 15.78. You can refer in the diagram in the right if you are having any trouble, especially since there are many values that are involved. So for streams, THP for the high pressure turbine and the TLP or the low pressure turbine. So we have our energy balances, and as you can see with our calculated values, the energies are negative, meaning that they produce energy. So again, we calculate the same method with the boiler and condenser heat energy. So for the boilers, which include the mainstream or stream 5 and stream 8, and the reheating, which is stream 9 and stream 10. So as you can see, the streams are positive, meaning that they require heat. And for the QB net, which is the total, it is 3,569, which is greater than W net, which is the net energy that is produced by the turbines and accounting for the energy consumed by the pumps. And usually this is not required, but we can calculate the heat that is produced by the condenser, which is negative 1835. However, it's usually not accounted for efficiency calculations. What are accounted, however, are the W net or the network and the net heat required. So for the thermal efficiency, we have negative W over Q, which is equal to 0.4858. So as you can see, it is not that too efficient, but rather it is actually quite low. We can also calculate the network or the net power rather by multiplying the mass flow rate to the specific work. So as I have mentioned in the problem, the mass flow rate is 42 kilograms per second. And multiplying that to the network produced, we have 72 kilowatts 72,000 rather kilowatts produced. To summarize the discussion, first we need to consider the reheat cycles, which involve reheating the first turbine outlet isobarically and feeding to a second low pressure turbine. Regenerative cycles, in the meanwhile, heat the feed water with steam from the turbine before boiling. There are two types, which is the OFWH and the closed FWH. The former involves mixing, while the latter does not. If you want to review more about the reheat and regenerative cycles, you can refer to these readings for your own convenience. And if you have any questions regarding this topic, you can also contact us on Gmail or Facebook, and our contact details are shown on the screen. But in the meantime, thanks for listening to this discussion and good luck in your studies, not only in term but for your entire chemical engineering career.